This conference will now be recorded.
All right, this is a video to go along with the notes we would have covered today in class. So we had a couple of examples from the last section I wanted to finish up first before we do the midpoint rule. So this is, remember, a definite integral, which means we're trying to do the integration on a closed interval, which means we have a lower and an upper limit. We learned that you take the antiderivative and you don't really need the plus c when you have a definite integral. And then we evaluate it at the upper limit minus the lower limit, and that gives us the approximation of the area of that region under that curve. So for this one, it looks like we need to think about a u substitution because this is being cubed. So if we let u equal 2t plus 3, then du would be 2 dt. So we need a 2 in our integral here. So to counter that, we'll put a 1/2 on the outside from 0 to 1 of 2t plus 3 cubed times 2 dt. So the 2 and the half counter each other. That makes this 1/2 0 to 1 of u cubed du. We would do the integration here. So that would be u to the 4th over 4. And remember, this says from 0 to 1, but that's only if you're in the original variable. So we need to change those back to 2t plus 3. So this would be 2t plus 3 to the 4th all over 4. And we need to evaluate that, remember, at 1 first and then 0. So you have your 1/2 out front, got a big parentheses. The first evaluation is 1, so that's going to be 2 plus 3 to the 4th over 4. And then we're going to plug in 0, which would just be 3 over 4, with the 3 on top being to the 4th power. So that is 1/2 5 to the 4th over 4 minus 3 to the 4th over 4. So that's 1/2 of, I don't know 5 to the 4th off the top of my head. I want to say it's 625, but that's a guess. Yeah, 625. So 625 over 4 minus 81 over 4, because that's 3 to the 4th. We'll subtract those. That's 544, and I'm going to go ahead and divide that by 4. I believe it goes evenly. Yep, so this is 1/2 of 136, which would be 68 units squared. So there is that one. Okay, let's look at the next one. I had a typo on this. I had it as -1 over x. That gives you an area that goes underneath the x-axis, which means the answer comes out negative. So if you tried that one, you're like, why is my area negative? It's because the graph is in the negative y values. So I changed it to a positive so that this will make more sense. So this is going to be, what is the integral of 1 over x? What is the antiderivative of that? That's just natural log of absolute value of x. And we're evaluating that from 2 to 5. So this would be natural log of 5 minus natural log of 2. So 5 natural log minus 2 natural log. That's going to be 0.91, so 0.92 if we round to 2 decimal places, units squared. So it's a very tiny region. Okay, and then that gets us down to, I wanted to do another average value problem. Remember, we had a formula for average value. It's 1 over the upper limit minus the lower limit, and then you do the definite integral. So this would be, if I want to find the average value, that's how I know I'm using that formula. It's 1 over 3 minus 0 of the integral from 0 to 3 of 2x squared minus 1 dx. So this is 1/3, 0 to 3 of 2x squared minus 1 dx. I'm going to take my antiderivative. So that's going to go up to the third. So 2x to the third over 3 minus x from 0 to 3. So I have my 1/3 out front, big parentheses, excuse me, 2 times 3 to the third over 3 minus 3. So all of that is actually the first evaluation. Then we have to do 0 into this. So that would be 2 times 0 cubed over 3 minus 0. And then, so what do we get here? So that is 27 times 2 is 54 divided by 3 is going to be, actually that would have been easier to just reduce this first. So that's 27 divided by 3 is 9, so 9 times 2 is 18. So 18 minus 3 for the first part. Then that'll be minus, and then this is just 0 minus 0. So it's just going to be 18 minus 3, which is 15. So it's 1/3 of 15, or 5 units. Or, sorry, not units. This is the y value. So just 5. Okay, this next piece is a formula. It's called the amount of an annuity. It says, now this is a formula that I believe, let me look at the review for the test. If we were to give you this on the test, I want to say we would have to give you the formula. So let me look and see if this one's even included on the exam. Because if it's not, we may just skip it in the notes for now and talk about it when we come back together on Tuesday after break. Yeah, it is in here, and the formula is not provided here. So I'm going to have to double check on the test to see if that's provided for you or not. So we do need to go through this. Okay. It's just the formula is a little long, so I always like to make sure it's actually on the test before we go through it. But we did see a problem that said find the amount of the annuity. So it says if C represents a continuous income function, so C of T is a continuous amount of money that you are putting into your account every so many months or weeks or whatever it is you're measuring your time by. And it's consistent. Okay, and that's in dollars per year, where time is years. R represents the interest rate compounded continuously. That's why E is in this formula. And T represents the terms of the annuity in years. Then the amount of the annuity is as follows. So it's E to the little r big T, the integral from 0 to big T of your amount that you deposited, and then E to the negative r little t. Now notice this is little t. This is your variable. The big T you're going to know, the little t you don't. And then it's in dt. So it says you deposit $2,000 each year for 15 years in an individual retirement account, paying 5% interest. How much will you have in your IRA after 15 years? So this would be E to the 0.05, because that's my rate. I'm letting it sit for 15 years, because remember, big T is the number of years. So that's going to go from 0, which was my starting point, to 15 years. The initial deposit that I make every year is $2,000, or continuous deposit, I should say. And then I have my E to the negative 0.05, and then this is little t. It's not the same thing as 15 years. And then that's going to be dt. Okay, the first thing I would do is I would probably pull this 2,000 out to the front, since it's just a coefficient. And I would go ahead and work out that 0.05 times 15, which is 0.75. That just makes this easier to write. Then I have my 0 to 15, e to the negative 0.05 t dt. Now, because that's not just a t in our exponent, this is a u substitution here. So u is going to be negative 0.05 t, because that's the exponent we're looking at. And that means du would be just a negative 0.05 dt. So we're going to need to multiply this by the negative 0.05. And then we need to divide to counter it on the outside. Okay, so then that allows me to rewrite this, and sometimes it's better to not work all of this out to the end because of the E being rounding, but sometimes it's okay just to work out the numbers if it comes out nice. So I'm going to just see if it does. So 2,000 divided by 0.05, and that's negative 40,000. That part at least will be easy to write. So this is going to be negative 40,000. I still have my E to the 0.75. I didn't want to round that yet. And then this is from 0 to 15 of e to the u du. So that's going to just be an e to the u, which we know our u was negative 0.05 t, because that's u. And we're going to evaluate that from 0 to 15. And we have this as our multiplier at the end. We're going to multiply it by negative 40,000 e to the 0.75. Okay, so the first thing I'm going to do is evaluate those two limits, the upper and the lower. And remember, we subtract in between them. That's how we evaluate the area. So this is e to the negative 0.05 times 15 minus e to the negative 0.05 times 0. So this guy is e to the negative 0.75. And this is just e to the 0, so this is minus 1. So I need to work that out first and then times it by everything up front. So we have 0.75, and that's negative, and that's e to that. You may enter yours in first, just depends on your calculator, minus 1 times the 0.75 e on the front, and then times that by negative 40,000. Oop, too far. So that is $44,680. Now, if you think about it, you deposited $2,000 every year for 15 years. So 2,000 times 15, that gets us to 30,000. So we earned, I'm just going to subtract backwards here, but this is supposed to be positive. We earned $14,680 in interest in our annuity. So that's pretty good. Okay, so we're going to do one more of these. It says find the amount of annuity with the income function C of t equals 5,000. So this time they actually say, hey, this is C of t, and an interest rate of 4, so that'd be 0.04, and for a term of 20 years. So that's big T. Sorry, I always want to write little t. So in this formula, the number of years they tell you is always big T. So this would be e to the negative 0.04. Oh, sorry, I think it's just regular RT. Yeah, see, I don't have this formula memorized either, so I'm going to double check to see if she has you guys memorizing this one. No, that's not what I wanted to do. Erase. No. All right. We'll do it the hard way. There we go. So it's just 0.404 times 20 on the outside, and then 0 to 20, then your amount, which is 5,000. And then this is where the negative exponent comes in. So negative 0.04 and then little t dt. So same steps as before. We'll pull the 5,000 out to the front. My PDF's having a little trouble. Just give it a second. Here we go. I'll go ahead and work out what 0.04 times 20 is. So that's 0.8. This is going to be 0 to 20 of e to the negative 0.04 t dt. You know you need a negative 0.04 here, so I'm kind of doing the u substitution in my head since this one's just a constant. And that means we need to divide by that on the outside. Works exactly the same as the last problem. So let's see if we can simplify that. So 5,000 divided by, I put multiply, divided by 0.04, and it's negative. So that's negative 125,000 e to the 0.8, and then this would be e to the negative 0.04t, just like before, even though it was an e to the u here, and that's from 0 to 20. So we already know that this is going to be e to the negative 0.8 minus 1, essentially, because e to the 0 is going to be 1, and this is going to be the same thing as this, but just a different sign. So let's go ahead and work that out. So this is 0.8, and that's negative with an e, and then minus 1, times that by the e to the 0.8, and then 125,000, that is negative. That gives us 153,193. So that's quite a bit of money. And you let it sit for 5 extra years this time. So notice you did 20 years and you deposited $5,000 every year. That's 100,000. That means this time you earned $53,193 in interest. So see, that's the power of compound interest. The longer it sits, the bigger the gaps get. Okay, so this very last section of notes before this, and this finishes us up for the semester. It's a way that I was kind of hinting at this in class about Riemann sums, and that's kind of how the whole area under the curve thing came about. So we're going to teach you just one way to show how to do rectangles for an area under the curve. It's called the midpoint rule. Essentially what happens is that you break up an interval, say from 0 to 2, into a specific number of rectangles. And then you figure out the area of each individual rectangle by knowing the width of the rectangle, which is how you broke it up into its intervals. And you need to times it by the average height of that specific rectangle. That is usually found at the midpoint of the rectangle. So I'm going to show you kind of this one without giving you the rule yet, then we'll give you the rule. I don't expect you to do all of this graphing pick part on the test. You would just break it up into the intervals immediately. But I want to graph x squared plus 1. So I'm going to plot that from 0 to 2. So if you plug in a 0, that just gives you a positive 1. If you plug in a 1, that would be 1 squared plus 1, so that's going to be a positive 2. If you plug in a 2, though, you get 2 squared is 4, plus 1 is 5. So notice this is part of a parabola, essentially. And if we kind of drop down, not so well that I did, we can see that this is the area that we're trying to approximate. Now they said to use 4 rectangles to break this up. So if you imagine that, you can think about drawing kind of mark at a half and at 1 and at 3 halves, or 1.5 and at 2. That would give you 4 different regions inside here. Now the rectangle would have to end on each of those, and it has to kind of go above or below the graph depending on where it is. It might be above sometimes, it might be below. I'm kind of drawing all of mine as above, just to kind of give you an idea of what this looks like. So each of these has an area because they're rectangles. They all have a width of 1/2 because that is exactly how we broke it up. We would said if you want to break it into 4 rectangles and your length is 2, 2 divided by 4 is 1/2. So that's how we get the length of each, or the width of every rectangle. To find the height, we evaluate the midpoint of each of those regions. So if we wanted to find each of those, we'd need to know what was the midpoint of each of the regions. So I'm going to write out what was each region first. So I had the region 0 to 1/2, and then I had the region 1/2 to 1. So this is my second rectangle. And then I have a region 1 to 3/2, and 3/2, or 1.5 to 2. So those are my 4 rectangle regions, essentially. Now, what we want to do is we want to find the height at the midpoint. So I'm kind of explaining to you how this rule works. So to do that, you have to figure out what's halfway here. Well, if this is 0.5 and this is 0, that would be 1/4 in the middle, or 0.25. So you're going to evaluate the function at 1/4. That will give you the height at that midpoint value, which tells us about the middle height of what the rectangle would be. This one would be one, and how you find a midpoint if you don't know it already, like I knew that was 1/4, is that you add these together and cut it in half. So think about this being 2/2. So that's 1/2 plus 2/2, that's 3/2. And if you cut it in half, that means you double the denominator essentially. So it's 3/4. So 0.75. This one would be 2/2 plus 3/2, so that's 5/2, and then it would make it 5/4 if we cut it in half. And this would be 4/2 plus 3/2 is 7/2, and then we cut it in half and get 7/4. So these are the midpoints of each one. So it's the middle, and it's just, and we're going to be estimating these, so it's okay if you go to decimals too. So you can just take your calculator, add those together, and cut it in half. So when we plug these in, you're going to notice you're going to get fractional answers, but we're doing an approximation anyways, so it's okay. So this is 1/4 squared plus 1. So that would be 1/16 plus 1. And then that would be 16/16. So that's going to be 17/16. So that's this evaluation. If you times that by remember, an area of a rectangle is length times width. So this is my length, 17/16. And my width is the width of each of those rectangles, which was 1/2. So the area of that first rectangle is actually 17/32. Okay, let's do the second one. So this is 3/4 squared, which means we square top and bottom. So that's 9/16 plus 1. 16/16 added to 9 would be 25/16. Then I'm going to do 25/16 times the 1/2 for my area of my rectangle there. And that would be 25/32. Do 5/4. So that's going to be 25/16, because you're kind of getting the gist, plus the 1, because we're using our function here. So 25 plus 16, I don't know that off the top of my head. I think it's 41. Yeah, so 41/16. Plus the 16/16 for 1. So that's going to be 57/16. So the area of this one is going to be 57/16 times the width of the rectangle, which is 1/2, or 57/32. So we only have one more to do. So this is kind of tedious, but you're going to notice in a minute that some functions we couldn't do without this method, because we can't use U substitution or anything we've learned so far. So this would be 49/16 plus 16/16, kind of jumping ahead. So 49 plus 16 is 65/16, and 65/16 times 1/2 is going to be 65/32. Now, to approximate the area, you add up all 4 rectangles. So I just need to add all my numerators and then divide by 32. So 65 plus 57 plus 25 plus, what was my first one? 17. So that adds up to 164/32. This is not wanting to cooperate. Hang on just a second. Okay, so we divide that by 32, and that gives us 5.125 for the approximate area. Okay, so that's after adding all those areas together. So we added this area to this area to this area to this area. So we did 4 individual rectangles of a very specific width, and then we found the height of each of those using the midpoint of each rectangle. So the question is, how good is that? Is that estimate pretty good? So since we already know how to do integration, we're going to show you the exact area of this region using our antiderivative rules. So we were doing from 0 to 2 of x squared plus 1 dx. So we would take the antiderivative of that. So that's going to be x to the third over 3 plus x from 0 to 2. So that's going to be 8 thirds plus 2, that's the first one, minus 0 thirds plus 0. So those cancel out essentially. So this is just 8 over 3, and I'm going to get a common denominator, plus 6 over 3. So that is 14 over 3. Now that's the exact answer. So if I divide that, we'll see if it's close to 5.125. And it was 4.6666. So did I do something wrong on the first one? It's always the question. It's very easy to make a mistake when your pen is going crazy. Let me add those again. So 17 plus 25 plus 57 plus 65. It's 164 divided by 32. Yeah, I'm getting 5.125. If I made a mistake, it's in the arithmetic somewhere. But here's the thing. This is a rough estimate. It's not going to be exact, but it's usually a little bit closer. So we're moving on. We'll just do the one that here's how you do the rule, because I don't want to re-record that whole problem. So to approximate the definite integral from a to b of f of x dx with the midpoint rule, use the steps below. You divide your closed interval into the number of subintervals they tell you to by finding this. This is called the width of your rectangles. So you subtract the high number minus the low number, and you divide by this number, whatever it is, 5 rectangles, 6 rectangles. That tells you how wide each of your rectangles is going to be. You find the midpoint of each of our little subintervals that we made. So you have to figure out what's the middle number of each one. And then this is a little bit different. So here's what they do. They take that width of each rectangle, because it's always the same, and you just go ahead and do all your evaluations and add them together and times it by the width at the very end. So instead of doing length times width, length times width, length times width, length times width, you add all of the lengths together and then times it by the width, because it's the same width every single time. So let's do another one. So this says our interval is 1 to 5, and we're doing 4 rectangles. So to find our delta x, or our width of our rectangles, that's what this is standing for, we would have to do 5 minus 1 on top, divided by 4. So that's 4 over 4, or 1. That's our delta x. That's how wide each rectangle is. So if we break this up in intervals, then you have to go from 1 to 2, because that's a width of 1. And then from 2 to 3. And then from 3 to 4. So we're breaking 1 to 5 up into 1 length intervals. And then 4 to 5. You find the midpoint of each of these intervals. And I'm okay with you writing them as decimals if they are. So if you want to write 1.5, that's okay. So 1.5, 2.5, 3.5, 4.5. Okay, so from 1 to 5 of 9 over x dx without using the actual antiderivative is approximately delta x, which is 1, times all of these in the function. So f of 1.5 plus f of 2.5, excuse me, there we go. So f of 2.5 plus f of 3.5 plus f of 4.5. Okay, so I'm going to have to work each of those out and add them together, and my function is 9 divided by x. So 9 divided by 1.5 is 6. So that one's not too bad. 9 divided by 2.5 is 3.6. 9 divided by 3.5 is 2. Let's round this to 4 decimal places. So 2.5714. And 9 divided by 4.5 is 2. Okay, so we're going to add all those together and then times it by the one width of all the rectangles. So 6 plus 3.6 plus 2.5714 plus 2. And then times that by 1 and it's still itself. So that's 14.1714. And that's unit squared. I didn't write that on the first problem, but it's still area. Okay, so this is another one I could have done by an antiderivative because we know how to do 9 over x. So we're going to show you the exact area doing the actual definite integral. So from, I believe it was from 1 to 5, not 0 to 5. So from 1 to 5 of 9 over x dx would be, I'm going to go ahead and pull out the 9. So that's 1 to 5 of 1 over x dx. That's a natural log function. So 9 times natural log of absolute value of x evaluated from 1 to 5. So that's going to be natural log of 5 minus natural log of 1. And natural log of 1 is 0. If you type it in on your calculator, you'll see that. So that's just going to be natural log of 5 times the 9. And that's about 14.4849. So you see it's much closer. Now, if you wanted the exact answer, you would actually have wrote this as just 9 natural log of 5, since the natural log of 1 is 0, because this is exact. Approximate means you went to decimal. Okay, so this is the whole point. This is what the midpoint formula kind of rule does. I omitted 2 of them because they're not on the test, but this one you wouldn't have been able to do using U substitution because it's x squared plus 1, and you don't have a 2. You don't have an x on top, so you can't use 2x as your, du. But you can actually do this one using the midpoint rule. So I'm probably going to write those up separately for you guys, just so you can see it. But it's not on the test, and neither is the square root, and they're not even the ones that are in the homework. The homeworks are all polynomials for the most part. So I'm going to do this one because this is in the review for your test, and I want you to make sure you have this in your notes. So at time t in seconds, the velocity v in feet per second of a car is given by v of t equals 3 plus 0.2 t squared for 0 to 6. Use 3 rectangles to estimate how many total feet were traveled during this time. So we're using the midpoint formula since they said use an n of 3. So again, this is your closed interval, 0 to 6. So we have to do 6 minus 0 to find, this is to find our delta t this time, over 3. So that's going to be that our rectangles have a length of 2. That helps you break this up. So this is going to be 0 to 2, then 2 to 4, and then 4 to 6. So there's my 3 different rectangles that I would use for my bases. The midpoints are nice here. This is a 1, a 3, and a 5. So those are my midpoints, halfway point of each region. So then we need to do 2, because that's delta x, times f of 1 plus f of 3, or I should call these v, I guess. Let's go ahead and be correct with our notation, since this is velocity, not f of x. So v of 1, v of 3, and v of 5, and we're adding those together. Because remember, this is just computing individual areas of each rectangle if we actually drew them out. Oh no. Hang on, I'm going to have to reopen the program. It's the only bad thing about using the PDFs. They don't like me. Actually, it didn't close, so we're just going to go with this. Get this one done. All right, so I need to plug 1. And remember, this is approximately equal to 0 to 6 of 3 plus 0.2 t squared dt. Okay, so put in a 1 into the function. that would be 1 squared, so that's just going to be 0.2 plus 3, so that's 3.2. 3 squared would be 9, so I'm putting it in the function, times the 0.2 plus 3, so that's 4.8. And 5 squared is 25, times the 0.2 and plus the 3, so that's going to be positive 8. We add all those together and then times them by the 2 that was the width of our rectangles. So 8 plus 4.8 plus 3.2, that's 16, times it by 2, and that gives me 32 feet. All right. So that is the end of this section of notes. Like I said, I'll probably write up 5 and 6 for you guys separately and bring it on the Tuesday after Thanksgiving. I'm going to create a little worksheet that kind of goes over the ones we did together, maybe just one of each type. I want you to complete that and bring it back on the Tuesday when we return. That way I know that you watched the video. All right, have a good Thanksgiving break.